Today's practical, we will be seeing voltage divider biasing circuit. The aim of this practical is to find the operating point, that is the Q point, both theoretically and practically. So let us first draw the circuit. So your voltage divider circuit is this. The voltage VCC is given as 10 volts. Resistance RC is 470 ohms. RE is 1 kilo ohms. R1 is 164 kilo ohms. R2 is 82 kilo ohms. So you need to implement this circuit theoretically and practically. The transistor is 2N22222A and the beta factor of this transistor is 220. During the simulation, I will tell you how to find out beta. So the first step for theoretical calculation, you will be going for theoretical calculation. Find out the value of VB and RB. RB is nothing but Thevenin's resistance, which is R1 in parallel to R2, which comes out to be 54.66 kilo ohms. VB is nothing but Thevenin's voltage, which is given as R2 upon R1 plus R2, which comes out to be 3.33 volts. The resistance over here, this is R1, this is R2. This resistance is RC, this resistance is RE, this is VCC. Okay. Now IB is given as VB minus VBE upon RB plus 1 plus beta times RE. This is equal to, substitute the values, you will get this value as 9.54 microamperes. Remember, this is current, so unit is microamperes. IC is beta times IB. So this comes out to be, beta is nothing but 220. So this comes out to be 2.09 milliamps. Lastly, you have to find out VCC. VCE is equal to VCC minus IC RC plus RE. This comes out to be 6.92 volts. Therefore, Q point is equal to 6.92 volts, 2.09 milliamps. After finding out the theoretical value, we will find out the practical values of the Q point using MultiSim. So let us make an observation table over here so that we can record our observations. Parameter, theoretical value, practical value. Parameter is IB, then is IC and VCE. Theoretical value of IB was 54 point 9.54. It is 9.54 micro. IC value was 2.09 milli and VCE is 6.92 volts. So now we will be finding out the practical values. To find out the practical values, you have to implement the voltage divider network using MultiSim. So here I have implemented it. I have put in the same values. You have going to the basic components. There you have a transistor. Select the transistors. So go to BJT NPN and then select transistor 2N2222A as the transistor for simulation purpose. Then to find out beta, double click on the transistor and there is edit model. You have different tabs. Go to edit model. In the edit model, BF, this BF that is ideal maximum forward beta 220. This is the value of beta which we have used for calculations. So you will be always using, in your practical purpose, you will be using this value of beta 220. And how to find out that? Go to edit model, click on that and you will see the value BF. Okay, edit model and find the value of BF, that is beta value practically. And after that, I think you know how to change the value of your resistors. I'll just change the label. This is RC. This is RE. So the practical circuit is here. It is ready to be implemented. Go to over here. You will be having interactive simulation. Click on that. Go to DC operating point and select the DC operating point which we have to see. But before that, just let me mark the nodes. Go to option, go to sheet properties, go to show all, click OK. You can see that your different nodes are marked. you have to find out the value of VCE. Let me write it in the text box. You have to find out the value of VCE. VCE is nothing but VC minus VE. So over here VC is the voltage at collector, which is the voltage at node 5. So it is voltage at node 5 minus VE is nothing but the voltage at emitter, which over here is voltage at node 3. So V voltage at node 3. So to find out VCE, it should be V5 minus V3. Now go to DC operating points. Let me remove this. I'll tell you. After your DC operating points, here are the different voltages, all variables. We have selected all variables. In this, there is different. You have current of the transistor base, current at the transistor collector, current at the transistor emitter, then you have the saturation current, current across the different resistors, voltages, P stands for power, and then the different voltages at different node. V2 is the voltage at node 2. But we have to find current IB and IC. So click on IB, add. You have added the variable IB, which you will be seeing in the output. Over here you have 3 tabs: output, analysis options and summary. Click on output and then add IB. Add IC also so that you can see the collector current. IB, IC. Next we have to see VCE. VCE is nothing but voltage at node 5 minus voltage at node 3. So add expression. In the expression, you can write it over here: voltage at node 5 minus voltage at node 3. This will give you VCE. Click on OK. You have added these expressions. So while adding these expressions at the output, you are allowing your MultiSim to do the DC analysis so that you get the base current, collector current and voltage VCE. Now you can save it. Again go to DC operating point. These are added. Just run it. You will get this table. So your VCE value is coming out to be 6.842. IB value is coming out to be 9.79 and IC is 2.14 milli. Okay, so these are your operating point practically. Now let us write the practical values over here. So IB practical value which you got is 9.79 microamperes. IC value which we have got is 2.14 milliamperes and VCE is 6.84 volts. There is a very important parameter which is called as percent accuracy. How much accurate values you have got? Percentage accuracy. So let us find out the percentage accuracy. Percentage accuracy is given as 100 minus percentage error. Percentage error is given as practical value. It is whichever is the highest, you will take that value. Practical value minus theoretical value upon the practical value. So if I am finding percent error for IB, it will be 9.79 micro minus 9.54 micro upon 9.79 micro. So this value comes out to be 0. So let us calculate this value. Since it is percentage error, it is multiplied by 100%. Multiplied by 100. So this value comes out to be 2.55%. Therefore, percent accuracy is equal to 100 minus 2.55, which is equal to 97.45%. So the percent accuracy for current IB is 97.45%. So the percent accuracy means how much your practical value is nearer to the theoretical value. So they are matching 97.45%. Similarly, you can find out for IC and BCE. You can also find out the Q point of other biasing circuit using the same DC analysis method. I hope this video would have helped you in some way or the other. Thank you.